The nearest star is Alpha Centauri, 4.37 light-years from Earth. Actually, Alpha Centauri is a triple star system, consisting of 3 stars: Centauri A, officially Rigil Kentaurus; Centauri B, officially Telemann; and Centauri C, officially Proxima Centauri. Alpha Centauri A and B rotate around a common center, whilst Proxima C is a small, red dwarf star. It is very unlikely any planets in this triple star system would be suitable candidates for habitation by man, because their orbits would be very irregular, due to the gravitational forces exerted upon them by the triple star system. We would have to look beyond them. Let us imagine that we wished to travel to Proxima Centauri. If we could travel at the speed of light, a return trip would take 4.37 years, even if no allowance was made for the time taken to reach this speed, and then to slow down. The fastest spacecraft yet developed by man is Voyager 1 and is currently moving at 1/18,000 the speed of light. At this rate, a journey to Proxima Centauri would take 80,000 years. Even if we could somehow increase the speed to 10% of the speed of light, it would take around 50 years to reach, and think of the huge store of life support materials that would be needed, from oxygen, fuel, water, food to communication, navigation and other systems, plus shielding from ionizing radiation, and spare parts for everything. At 10% the speed of light, the collision with interstellar dust would cause considerable damage to the craft, due to the high relative speeds and large kinetic energies involved. Also, experiments by the Smithsonian National Air and Space Museum indicate that after just 6 months of travel, an astronaut loses 10% of his bone mass, which takes around 4 years living on Earth to replace. A traditional spacecraft approach to explore space, given the insuperable challenges faced, must be realized as an impossible dream. If humans want to travel in space, they must think long-term. After all, evolution took billions of years, so does the formation of stars and galaxies. Nature and evolution are long-term projects. We are not going to conquer interstellar space using a spaceship equipped with radiation shields, a treadmill helping toward a bone loss through exercise, and some pills to counter boredom. What is needed for space travel? 1. Protection against radiation. 2. A normal environment. 3. Adequate supplies of everything. 4. Protection against everything from interstellar dust to small rocks. 5. A propulsion system. 6. Gravity. 7. Oxygen, water, air. 8. Farms to produce food. 9. Everything, and a whole lot more. The early humans journeying forth into interstellar space will be certain in the knowledge that they will never be returning to Mother Earth. For them, and their ancestors, it is a one-way trip. For these humans to function normally with this knowledge, they must have access to a whole range of things, from the ability to make relationships, venues for enjoyment, protection against others, good food, clean air, a purpose in life, ability to pursue interests, privacy, access to knowledge, a judicial system to resolve disputes, a fully equipped hospital to take care of illness, a sanitation system, a sports venue, schools, etc., etc. Without this infrastructure, they will evolve into something less human. These interstellar explorers must be self-sufficient in every way. They must have the capability to manufacture and invent, because many inhabitable worlds they may encounter will demand coping and adaptation strategies that humankind has never before encountered. Flexibility must be the key thought for planners. It would take a lot of resources to create a space vehicle with all the attributes needed. It would have to be huge, really huge. In fact, so large it would be impractical to build, and beyond the resources of any single country. What is needed would be a space vehicle that is already billions of years old, so has already been tested, in that it has withstood radiation, meteor strikes, and interstellar collisions. What is needed is a small planet. The interior would supply protection against radiation and small rocks and interstellar dust, as well as providing insulation against cold. The material from which the planet is made can be mined and processed, and will assist self-sufficiency. The interior of a planet can provide room for Earth-like facilities such as those mentioned previously. The planet could be given an artificial spin to simulate gravity. The catalogue of minor planets within the solar system is published by the Minor Planets Center. The published number is over 500,000. As of April 2019, there are 523,824 numbered minor planets out of 789,069 observed planets. It is expected the upcoming survey by the LSST will discover another 5 million minor planets over the next 10 years. Something around 1,000 kilometers in diameter may be ideal. This would provide internal space for a city, mining operations, and all the infrastructure needed to make the population self-supporting. It would also provide the raw materials. Most planets are made of rock, containing common minerals like feldspars and metals like magnesium and aluminum. NASA is forging ahead with experiments that will try to extract hydrogen, water, and oxygen from the Moon, and it is believed many small planets may have frozen water on their surfaces. How to capture a small planet. Solar electric propulsion may be the ideal way, using the energy from the sun. Electric propulsion can achieve high speeds over long periods, and are cost-efficient, requiring little or no maintenance. Electric propulsion is now a mature and widely used technology on spacecraft. Over 200 spacecraft use electric propulsion to keep station, to change orbit, or for primary propulsion. If the small planet has a magnetic field, this may also be used as an energy source, as could solar sails. How long would it take? This very much depends upon the location of the small planet, but even if it takes 100 years, it doesn't seem too long in terms of man's efforts to conquer space to date. Once set up, the system would be a combination of automatic control and human control from Earth. The planet may be accelerated by equipping it with solar sails. Voyager 2 famously used gravity assists to visit Jupiter, Saturn, Uranus and Neptune in the late 1970s and 1980s. Cassini used 2 assists at Venus and 1 each at Earth and Jupiter in order to reach Saturn. Where should it be parked? At the Lagrange point, which is a location in space where the combined gravitational forces of 2 large bodies, such as Earth and the Sun or Earth and the Moon, equal the centrifugal force felt by a much smaller third body. The interaction of the forces creates a point of equilibrium where a small planet could be parked whilst it is undergoing internal remodeling and fitting out. There are 5 Lagrange points around every planet or star. These points are named after Joseph Louis Lagrange, an 18th century mathematician. How far to a Lagrange point? It's around 1 million miles. In 1969, Apollo 10 achieved the fastest speed ever achieved by a manned vehicle at 24,790 miles per hour. 39,895 kilometers/hour, so a spaceship traveling at 25,000 miles per hour would take just over a day and a half to reach a small planet parked there. How long to ready the planet? It's difficult to give an exact figure, because it would depend upon so many factors, such as budget, commitment, availability of resources, etc. If a ballpark figure of between 75–100 years was aimed for, it would mean that in just over 2 human generations, the planet could be available for operational use. It may not be too long. When it is considered the planet would need to be self-sufficient in everything, including robotic probes to sample the atmosphere and surface of any potential planet, and such self-sufficiency should last at least as long as 10,000 years, twice as long as mankind's earliest known writings. How could the money be raised? Probably via a mixture of income streams. In 2018, about 142.86 billion gallons, or about 3.40 billion barrels, of finished motor gasoline were consumed in the United States, a daily average of about 391.40 million gallons. A 1-cent future tax on each gallon would yield around $4 million a day. Many people see space exploration as something worthwhile, as it may preserve the future of the human species, so there will be donations, bequests and possibly additional revenue from other sources such as advertising in space. Perhaps rent out some space for manufacturing projects? What's the point? Humankind doesn't have a backup system in place once humanity ceases to exist because of any number of reasons: disease, war, nuclear catastrophe, asteroid impact, artificial intelligence running amok, creation of hostile synthetic viral organisms, climate change, manufactured micro or black holes and vacuum decay, the eruption of a supervolcano that would fill the atmosphere with ash, sulfuric acid, and sulfur dioxide, and could potentially cause, and actually has, in the ancient past, a new ice age. Others, including the Astronomer Royal, have warned that subatomic particles called strangelets could be created accidentally. Strangelets are a hypothetical form of quark matter that in specific conditions could trigger a chain reaction to convert everything else to strange matter and destroy the planet. It should be remembered the average lifespan of the mammalian species is only about 1 million years.